Hey there, Calc 3 folks, back here with I was hoping I could say another quick video lecture, but this one might be a long one, so I do apologize. I may have to also put a couple of pauses in it. Hopefully you don't notice those pauses. I'll try to do it at good transition points here in the material. But again, I apologize ahead of the time for this being perhaps a little long and lengthy. And keep in mind, I am posting all these notes along with the videos to Blackboard so that you can certainly go back and get the notes and not have to spend your time writing all this out as we go through it, folks. The big thing you want to keep in mind outside of these lectures is that you're practicing these ideas, folks. I can talk to you all day long on this, and it's not going to help you learn it. What's going to help you learn it is by putting in that time and that practice, as I've hopefully illustrated in classes that through 10,000 hours of practice, which you can kind of say that I've chalked up under my belt, that certainly it's going to improve. It's going to help you improve your skills. I am no miracle worker here. I've just spent the 10,000 hours I needed to practice in calculus to master these skills. So again, folks, I'm hoping that you're out there just not watching these videos, but that you're also putting in that time to practice. All right. So I am going to start my lecture here over 16.4 material, where we are transitioning over into triple integration. We are still looking at that topic of chapter 16, focusing in here on that study of multiple integrals in our study of calculus here, where the first three sections we were studying the double integral in both the rectangular and the polar context. And we are now continuing that over into a study of one more iteration of integration applied to the doubles, and that being triple integration. And where I do start off with this this lecture, folks, is I go back to kind of how I started off with double integrals. I take note that this operator, known as the integration operator, actually is going to come in a couple of forms. It might appear as what we call a single integral operator, or what we would refer to later on in chapter 17 as a linear integral operator. It can appear in what we call the double integral form, the double integral operator, which we're going to learn also later on in chapter 17 can be referred to as the surface integral operator. And now what we're going to be introducing in section 16.4 is this operation known as triple integration. We're going to be applying the triple integral operator to functions. And we're going to learn in chapter 17 that this is also known as a solid integral. Right? We've gone from linear to surface to now solid integrals in our calculation, folks. In a sense, we're going to be performing integrations here that are going to be occurring across solids that exist in three-dimensional space. And as you might be picking up as a bit of implicit information in the background is that these ideas do extend, these ideas do extend up into the n-dimensional description of space, that we have really only in calculus 1, 2, and 3 spent our time in descriptions of space that go along with 1, 2, and 3 dimensions. If you go on to study calculus beyond Calc 3, one of the classes you might take is an advanced calc class, where you will consider these topics in an n-dimensional system, right? So it's good to be making these connections now between what we've seen here in 1, 2, and 3-dimensional space extending upward, right? Now, where we do begin is we consider, go back, we have to the beginning of double integrals, and that we have considered applying this linear integral operator to a multivariable function. And what we saw back in the beginning of double integrals is that when we apply this single integral operator, the linear integral, to a multivariable function, it does yield another function. If our integration happens with respect to x, and we're dealing with a multivariable function involving x and y, the result is going to be a function in terms of y, right? In terms of the variable y. And what we had noted back at the beginning of double integrals is that g of y is itself what we call a net area function. It's a function that describes the net area trapped between the xy plane, right? Or we might, the xy plane, right? For over values of x in that plane that run from A to B at some specific y value. All right? We did show that g of y came from this calculation of f at b, big F of b, comma y, minus big F at a, comma y, right? Where when we think about big F, right, big F's first partial with respect to x, right, does yield us the description of our surface z equal to f of x comma y in three-dimensional space. All right, we saw this as our opening to the idea of double integrals back in section 16.1. All right, let's take this a little further, I believe. Let me bring up my next note here. Similarly, we can go on to say, if we consider applying a linear integral operator, right? Notice again here, I'm taking this idea of linear integration, again, this single integral operator, and we apply it to a multivariable function f contained in three-dimensional space again, but we apply it across bounds now that are functional bounds, right? Where you can see here, I have kind of reversed around our integration. I kind of have set this up to have an understanding that is a little bit more along the lines of what we understand as double integration up to this point. And that is if we consider integrating function f, right, this multivariable function, first with respect to variable y, where y occurs across these bounds from g of x to h of x, how we think about that result, right, is that result is again another function of x, right? It's going to be itself a function of x, a lot like this integration up here produced this function of y when we integrated that multivariable function f of x comma y with respect to x. If I now come back and consider integrating, as we did in this case, with respect to y across these variable bounds, what that is going to produce in turn is a function of x. All right? Where does that function of x come about, right? It does come about from this difference, where again, big F, when we think about big F in this case, big F is the function whose first partial with respect to y gives us little f of x comma y, right? Where what big G of x does describe is again another net area function, all right? It's a net area function in this case, right, that occurs at a specified value of x in the two-dimensional system, where at that specific value of x, y is going to vary between these functional descriptions. In terms of x, y is going to vary between function g of x and function h of x. All right? But nonetheless, what we do note is that if we did come back and consider finding the single integral operator applied to this multivariable function, little f, in terms of y, right, across these variable bounds, it does produce, as we understand, a function of x. All right? Now, let's add another idea here. Now consider applying, in this case, the double integral over region R with respect to the area of R, right, to what would be a multivariable function f that it would exist here in four-dimensional space. This multivariable function f that exists in four-dimensional space is going to define what we call a hypersurface in 4 dimensions. It's not a surface that we can visualize, right, as we can only visualize 1, 2, and 3-dimensional space in the universe that we exist in, right? But there are dimensions that exist beyond 3 dimensions where we could consider having surfaces in those dimensions of space, which are going to be known as hypersurfaces. All right? So here we're considering the first case of a hypersurface that's occurring in 4-dimensional space. Notice it is a 4-dimensional relationship. It is a relationship here that involves the 3 independent variables x, y, and z, right, which describe a domain in 3 dimensions, and then our one output value w here occurring out and being defined within the fourth dimension. All right. Certainly we can visualize our domain still in the understanding of this multivariable function, but what we can't understand or can't visualize is necessarily how that domain and that range value, that value found as an output of this functional relationship, the dependent value, exists together in a four-dimensional space. All right. Now, in this case, again, we are going to consider applying this double integral R over what we have as rather a classical understanding, right, of R, where x is going to vary between the constant bounds of a and b, and y is going to vary between these functional bounds. All right. If we consider that application and taking from what we understand above in the previous two notes that I've developed, what we might note is this, or what we have here, folks, if we take note, right, is that this double integral operator, right, over region R that happens with respect to the area of R, applied to this four-dimensional multivariable function, right, this hypersurface, right, will yield this result in notation here, seen on the right-hand side, where if we approach this using iterative integration, integrating first on the inside of this iteration of integrations, these iterations of integrations with respect to y, we're going to see a result very similar to what we saw just above in our second note that we opened with. Except this idea here that we saw above is now going to be extended out into the case for little f of x, y, and z. Where if I consider integrating with respect to y in this case, right, across these variable bounds, what it is going to leave behind is another function. In this case, it's going to leave behind a function that involves the two remaining independent variables x and z. Since we integrated with respect to y, right, variable y is going to be evaluated across, its antiderivative will be evaluated across these bounds from g of x to h of x, right, where in the end, when we perform the definite integral process and integration, we do end up with this, what we think of as multivariable function in terms of just x and z. And I call it big G of x comma z to relate it back to this big G of x we've seen prior. Right? Where what we would note about big G of x comma z, it is a multivariable function that comes about by evaluating what we think of as big F being a multivariable description, right, of the antiderivative of little f. It is a multivariable function in four-dimensional space defined in terms of variables x, y, and z, whose first partial with respect to y yields us the surface, that the multivariable surface, right, that four-dimensional surface, that hypersurface that we're integrating across in our double integration. All right. Note, if we apply the double integral operator to a four-dimensional surface, the first iteration of integration is going to produce this result. Where now we're going to come back, well, and I should say where we have this understanding about its integrand. All right? What we're now going to consider coming back to is finishing this calculation. Consider coming back and integrating now across values of x on these definitive bounds from a to b. We're going to come back and put this first idea into play. If we do that, let me bring this note up. And we consider the value then for this integral seen here. As for the integral from a to b for that multivariable function big G of x comma z, all integrated with respect to x, right? We're going to see a result very similar to what we've seen above. Now, we are running out of function names here, folks. in order to keep us from confusing one function from another in this this bit of notes here, what this does result in the end, we note down here, is big M of z. It is going to define for us just a function, right? That's going to be in terms of the remaining variable in our multivariable function, right? Here, z is going to remain once we integrate with respect to x. How we obtain m of z is it is this difference given here. It is big H at b comma z minus big H at a comma z. Where big H, right? Big H we understand is the antiderivative function for function big G. Big H is a function whose first partial with respect to x, it is a multivariable function whose first partial with respect to x yields the argument seen in our integration above, the integrand given by big G at x comma z. All right? So, again, we end up with this, well, I should point out this value here, m of z, this multivariable function in terms of z. And I do think I make a couple of notes about m of z here. All right? Big notes in terms of what we've done above, right, in terms of the bigger picture here in this note, implying when a double integral operator that occurs over region R, where region R is described down below, is applied to a multivariable function, this hypersurface contained in four-dimensional space, the result is a function, right, in terms of just variable z, the one variable left over that we did not integrate with respect to when we perform this double integral operation over region R, right? Where big M of z, what big M of z describes is what we call a net volume function, right? It is what we refer to as a net volume function. Now, this is a bit analogous to what we had noted up above here. In this case, this big G of x that we had when we applied the linear integral operator to just f alone is that the multivariable function f in three-dimensional space, its result was a net area function. All right? Here we're still getting a functional result, but it's not going to describe a net area anymore trapped in that space. What it's actually going to describe is a net volume trapped in that space. All right? I do think I go a little further talking about this net volume if I bring that note into view. All right? This function m of z yields the net volume trapped between region R and what we think of as this hypersurface given by our four-dimensional function big F at x comma y comma z at some arbitrary value of z. Right? For values where z is specified to be equal to z sub null, right, or z null, m at z null describes the net volume trapped between the region R we might point out is contained in two-dimensional space, and some specific surface, right, defined by this multivariable function here, defined by w, again, where w was our multivariable function x, y, and z, where the z value is now specified to be z null. What this results in is, in a sense, we might say is going to be a result that is a multivariable function in terms of just x and y, right? That is actually contained in three-dimensional space. All right, so m of z would describe the net volume trapped between the xy plane over region R and what would be this description of our hypersurface, right, when the variable z in our hypersurface is designated to be the value z null. All right? Now, as previous similar results have implied, with the result m of z, and integration with respect to z can actually be applied. As we had noted back in our case for setting up double integrals back at the beginning of this chapter, right? With this result m of z at the end of this double integral applied to this multivariable function up above here, right? We are going to be left with this function in terms of z, where you can now come back and integrate that all with respect to z. And we could integrate that with respect to z across some variable bounds or with respect to some constant bounds. And I'm going to consider it here with respect to some constant bounds. Right? In this case, m of z, right, equal to this result here, right? I should say in this case for m of z, which equals this result here. The third iteration of integration would be denoted as this here. Right? That integration from c to d applied to m of z dz, all happening with respect to z, would be like applying this single integral operator to this double integral operation that we performed above. Right? Where this single integral operator with respect to z applied to this double integral operator is what's going to form what we understand as a triple integral. Right? Where we can start to see that triple integral setup, where we might notice or note where since r is defined as what we had noted above given by this, in this particular case, the single integral operator applied to z then would result in this triple integral here that we could define. Right? And that is illustrating what we say is a triple integral. Right? What I do point out is this result illustrates what's known as a triple integral, this result right here. Right? A triple integral of that multivariable function w equal to f of x comma y comma z that occurs over what we say is a region D that actually defines a solid region of space in 3 dimensions. Where in this particular case, D, that 3-dimensional description of space in 3 dimensions, right, is given by these coordinates x, y, and z in 3 dimensions, such that we've put these limitations on x, y, and z. It is the coordinates formed by the intersection of a values being stuck between a in value and b in value, or I should say x values being stuck between values of a and b in value, y values being stuck between functions of x, g of x, and h of x, and z values being stuck between constant values of c and d. Right? This is one specific case of what could be generalized, right, as what we just know as a generic triple integral of f over d contained in R3. Triple integral of f, we might note, well, actually, f can be any dimension. It's d that's going to be contained here in 3-dimensional space. Right? Where that formal definition, if we bring that into view now, is given in this theorem. Right? Which begins by saying this. Now, folks, what this illustrates is what we might say is our fundamental generic description of region D, right? What we're going to see develop here is that there's a lot of ways to define D. This region in 3-dimensional space above, I had defined D as this statement here, right? To bring about an understanding of the triple integral over D. But what this is here is a more specific scenario of what could be generalized here in our theorem. All right? Here in our theorem, we are assuming that we have this multivariable function contained in 4-dimensional space, right, is a continuous function over this region of D defined in 3 dimensions, where D is this set of points in 3 dimensions, where we're looking at the intersection of values of x between A and B, values of y between functions of x, g of x and h of x, and values of z actually between functions of x and y, m of xy, and what we see is n of xy on the upper end, right? Where these functions g, h, m, and n are themselves also continuous functions, right? So that's our assumption. We start with that setup. Then what is true is that f is going to be integrable over region D, meaning we can integrate it over this 3-dimensional region of space, where this integration is described by the triple integral that we denote down here, right? If I scroll up, bringing that triple integral into view, right, we have the triple integral occurring over region D, applied to function f happening with respect to the volume of D, right? What we will note here in a moment is that v represents volume, right? The volume parameter in our 3-dimensional space, where with this understanding of D, this is our triple integration in its specific format with regards to the specifications on D, right? If our specifications on D are given here, right? A being bounded, or careful there, x being bounded between A and B, y being bounded between g of x and h of x, and z being bounded between these functions of x and y, m of xy and n of xy, then this triple integral stated in general here is equivalent to this specific format, where you can see we are integrating 3 times across this function f, where that order is happening very specifically. On the inside, the integration is happening first with respect to z, right? Z being bounded by these multivariable functions of x and y, the 2 remaining variables that will be left behind in our integration, right? Once we integrate this innermost integral with respect to z and evaluate it across these multivariable bounds, we then integrate with respect to y, where y happens across the bounds from g of x to h of x. That is our, what we might say is our middle integration happens with respect to y. And then our outermost integration, the last integration in our iteration, would happen with respect to x, where x occurs across these bounds from a to b, across these constant set of bounds. All right? Which you may have noticed in the example above, not only does x happen between a and b, but z happens between a constant set of bounds from c to d. And as we saw back with double integrals, you're always going to want to end your integration on a set of constant bounds, right? That if you have integrated, all your previous integrations are all happening with respect to the variables of your function, ending on a constant set of bounds will give you a definitive value, a definite value in your integration, a real number value, right? If you have more than one set of constant bounds, those constant bounds integration, the integration of the variables across those constant bounds, can actually happen in any order. And what we actually see here is up in this example that I opened with is a little application of Fubini's. Right? Not only is x happening between the constant bounds a and b, but so is z happening between constant bounds of c and d. So I was able to actually integrate lastly with respect to z here and consider my first integration happening with respect to y. And not only can I have z be the last in the integration here, I could actually have x be final and have z occur before x if I wanted. All right? Again, illustrating a bit of Fubini's there. All right. If we take this a little further, if we take note on what is this all interpreted as, let me bring that into view here. To finish this theorem, we will note this result when we perform this multivariable triple integration here. It yields what is called a net hypervolume, right? It's a volume of space that exists or describes a space beyond 3 dimensions. It's called a hypervolume of space. It's the hypervolume of space, what we refer to really as a net hypervolume. Going back to that, when we perform integration, we're going to have areas or volumes, or now the case of hypervolumes, forming above and below in space, right? Above and below this region where that multivariable function could be positive or negative. Above and below what we might say is the region over which it's being integrated. So here in hyperdimensional space can occur above and below this solid of D, where some of that volume accumulating above it would be considered in the positive direction, and some of that hypervolume being accumulated below it would be occurring in the negative direction. And we have this concept of, well, some of the positive will cancel with some of the negative, leaving behind what would be considered the net value, right? And here it is going to be this net hypervolume. The net hypervolume trapped between this hypersurface, that surface being that 4-dimensional surface, right, and region D, this 3-dimensional solid, right, that exists here in 3-dimensional space. Between a 3-dimensional solid in 3-dimensional space and a hypersurface out there in 4 dimensions, there actually exists what we call a hypervolume of space, right? And this net hypervolume is measured in a units given by units to the 4th power, or what we call quartic units, right? Volume is measured in cubic units, area is measured in square units, length is simply measured in units. In this case of hypervolume, it's measured in quartic units, or units to the 4th power, right? I do have a couple of notes over this. First, let's consider just a quick calculation. As for calculating a triple integral, similar to calculating a double integral, it is an iterative process. As I've kind of highlighted, you start with your inner integration, move to the middle integration, and then end with the outer integral in the calculation. Excuse me. If we bring an example into view, right, we might consider this triple integral given here, right, where we're integrating this multivariable function given by x plus y plus z, first with respect to z across the bounds from 0 to 5, then with respect to y across the bounds from 0 to 2, and lastly with respect to x across the bounds from 0 to 1. What we do note is all of our bounds are describing constant bounds. And if we think about this solid in 3-dimensional space, this would actually be a cuboid in 3-dimensional space, right? The dimensions measured along the z-axis would go from 0 to 5. The dimensions measured along the y-axis would go from 0 to 2. And the dimensions along the x-axis would go from 0 to 1. In a sense, what we might say length of this cube would be 1 unit, the width of this cube would be 2 units, and the height of this cuboid would be 5 units. Right? It would have an overall volume of this cube given by 10 units cubed. All right? What we're going to do is integrate across that solid region of space between it and this multivariable, this 4-dimensional surface, this hypersurface, described by x plus y plus z. What we might even understand that as is that is a hyperplane, this surface, right? So if we take note and we, consider that integration, this integration first occurs with respect to z, right, across these bounds from 0 to 5. With respect to z, x is a constant, so its antiderivative would be x times z. Y is a constant, so its antiderivative would be y times z. And with respect to z, right, z is a variable, right, function. It follows the power rule. So z to the first power, so it bumps up to 2, and we divide by 2. That becomes 1/2 z squared. If we now evaluate these bounds across values of z from 0 to 5, certainly we can see plugging in a 0 into all our locations for z will zero this away, right? This would become 0 when we evaluate it at 0. But at 5, this first one will become 5x, the second term will become 5y, and our third term would become 5 squared divided by 2, or 25 halves. All right? So that's what my next line of note illustrates here. If we bring that into view, all right, what we end up with is this result here, which is now just a double integral, right, across this multivariable function, right? That's going to happen as we have ordered here from y, first with respect to y and then with respect to x. Now, as Fubini's has suggested, we can actually, because these are all constant bounds, actually integrate in any order that we choose, but I'll stay with what I have set up here, right? A more traditional order, first with respect to z, then with respect to y, and lastly with respect to x. Where if I find now this double integral, this integration first with respect to y, if I find the middle integration up here in our triple integral, well, that's going to treat all of our values in here as a function of y. So 5x would be a constant. That would become 5xy. 5y, y is the variable, so that would become 5 halves y squared. And 25 halves is a constant, so that would become 25y. 25 halves times y. I do take that note, and we're going to evaluate that across the bounds here from 0 to 2. And we get this result. Right? This was our antiderivative statement that I rolled through there. That's 5xy, 5 halves y squared, 25 halves y. Right? We get those respective results down here. Where if I evaluate from 0 to 2 now for y, plugging in 0 for all our y's, we'll have that 0 away. But substituting in 2 for y, this y will make that 10x. We see that down below here. Substituting in 2 for this y will make that 2 squared, or 4 times 5 is 20 halves. Well, 20 halves is just 10. And substituting in a 2 for this y, we'll actually have it cancel with the 2 in the denominator, leaving behind just 25. So if I simplify that integrand in terms of x, we end up with 10x plus 35, which is now just a single integral with respect to x that we evaluate across the bounds from 0 to 1. This x bumps up to 2, and we divide by 2. This becomes 5x squared plus 35x. If I bring that note into view, right, we do end up with this antiderivative of this statement here, which is 5x squared plus 35x. And if I evaluate it across the bounds from 0 to 1, at 0 it becomes 0, but at 1 we would end up with 5 plus 35, which is 40. And what we keep in mind here, folks, is what we're calculating is a hypernet volume. That hypernet volume being measured in units to the 4th power, or quartic units. So this is 40 units to the 4th power. All right? That would be this measurement value. And the actual value of the integral itself is just 40 units, right? Or 40 in value. I should say 40 units to the 4th if we consider its geometric interpretation. All right, that is the triple integration process. Again, it is a lot like the double integral in terms of it's an iterative integration process. You do need to pay attention to your order of integration there, right? And what would be the antiderivatives of your integrand in each iteration. But it is a fundamental process, folks. It is just repeating that fundamental integration process here 3 times. In the order first with respect to z, then with respect to y, and then with respect to x. All right? Now, I do have some, like I said, other notes to go along with this. Let me bring in some notes here. Note, to begin with, the triple integral, right, over the solid D in 3-dimensional space, right, for this multivariable function, this 4-dimensional surface, hypersurface, right, with respect to this variable v, right, denotes, right, or I should point out, is where this value of v denotes the volume parameter, right? We are performing an integration that happens with respect to volume, right? Where this dv, this differential with respect to v, we say, represents what we call an infinitesimal change in v. And I think I have that spelt right. My spell checker ran through and ran that all right. So what it is this very small change in volume. We are integrating over very small changes in volume here, right? That happens within region D, this three-dimensional solid of space, right? Within region D, that is, we might point out, contained in three-dimensional space, right? Which really does summarize what we think of as the products of dx with dy with dz, right? That dv given above summarizes this product of dx, dy, and dz here. Where what are dx, dy, and dz? As with we saw with double integrals, dx, dy, and dz represent little infinitesimal changes in our variables x, y, and z. If we make small infinitesimal changes in variables x, y, and z in our integration process, we are in a sense making a small infinitesimal change in volume. And our integration can be generalized to an integration that happens over some solid with respect to the volume of that solid. Right? And that's how we generalize triple integrations. Right? There is another note I'll bring in here. And I do say, as with double integrals, the order of summarized by dv depends upon how region D is defined. Right? As we had noted in our theorem, when region D is defined in this manner, we're up here in the theorem, then our triple integration for that calculation given here is as follows, where dv happens in the very specific order, dz, dy, dx, and our integration bounds appear as noted in the theorem. Right? Now, the summary given by dv really depends upon how we define region D in three-dimensional space, right? With the values of dy, dz, and dx, right? With these three values of the differentials, there are 6 ways that we could actually think about defining region D in general, right? And have an order summarized by dv. All right? There's going to be 6 ways we could actually consider generalizing our triple integration. Just like we saw back in double integrals, for dx and dy, there were 2 ways depending on the order of dx and dy. We saw one for the order dy dx, and we saw another case for the order dx dy. Right? We are going to start with our understanding of what we see in the theorem. Right? As presented in the theorem, defining the triple integral, right? dv would be summarized by dz, dy, dx, when D was summarized in this manner here as this region of space in 3 dimensions formed by the intersection of x between these values of x from a to b, y between these functions of x from g of x to h of x, and z bounded between these values of multivariable functions m of x comma y and n of x comma y. Right? Where we should point out in our understanding here is that in this case, D is a region of space in 3 dimensions. It's a solid region of space. It is a, we might say here, solid region of space in 3 dimensions, right? Where this solid is forming between 2 surfaces. It's forming between these 2 surfaces, m of xy and n of xy, over region R, where region R is defined as the region of space in R2, forming between these curves, g of x and h of x, over values of x that happen in this closed interval from a to b. All right? In terms of generalizing here our understanding of D given in the theorem, right, we could generalize our triple integral over region D for function f of x comma y with respect to the volume of D given in our theorem as this calculation here. Right? As we had noted, it really is just our double integral over R, right? Where that is being performed on what would be the single integration of our multivariable function f in four-dimensional space, that hypersurface, across these surfaces, right? M of x comma y and n of x comma y in 3 dimensions. Right? Which is an integration occurring over region D, illustrated as the following solid. Here's the illustration of what we're calculating in our theorem. Right? Or really what I should say is the region over which we're calculating in our theorem. We can't really illustrate the hypernet volume, but what we can illustrate and understand is this region D over which we're integrating. All right? This region D over which we're integrating here in this picture, if I blow this up a little bit so it's a little clearer to us in the video, right? This region D is a solid of space that is forming between these functions n of xy and m of xy. M of xy on the lower end, n of xy on the upper end, right? These z values are always going to be bounded between these two surfaces, right? We see that laid out here in our definition of D, where the other region identified, the other intersection between x and y's bounds, illustrated by the defining region of D, is what we describe as this region of R here in 2 dimensions. Right? This solid D forming between these two surfaces in 3 dimensions that we're integrating over with respect to in our triple integral is actually a solid forming between these two surfaces over this region of R. Where R is occurring, right, across some functions of y from g of x to h of x. G of x in this picture we might actually say is this line here, and h of x in this picture would be this line here, across bounds from a to b for x, where a might be this line here, and b would be this line here. Those bounds on x and y defining this region R down here in 2 dimensions. Right? When we think about a triple integral calculation as we've defined in our theorem, right, it could be thought of as this here, which has this understanding or this illustration, right, in terms of its understanding. Right? Now, I point this out for our theorem because I said our theorem is one illustration of what is 6 different possible organizations of that value, or summarizations of that value. We call the differential of the volume parameter, the dv value, right? We're not going to illustrate all 6 understandings. We're going to illustrate the first understanding and understand that this does reorientate itself with respect to these values of x, y, and z for the other 5 illustrations. All right? Otherwise, folks, this set of notes would be terribly long. Right? What we do here is we do want to have one fundamental understanding that we can extrapolate our understandings out for in the other 5 cases. All right? So let me bring up here the 6 cases we can have organized here. All right? As for the 6 orientations for defining D, right, and the description of dv, right, as for defining D, and I maybe should say here, and summarized by dv, right, are given as follows. Or, well, I'll just say are as follows, right? Here's the first case, right? This is what we see in the theorem. If region D is defined as this space, right, x between a and b, y between functions of x, g of x and h of x, z between these multivariable functions m of xy and n of xy, then dv is summarized as this, dz dy dx in our order of integration. Whereas one thing we could consider doing here is swapping x and y's roles in our description of r. In our second setup here, what you will notice is that y is now being considered to be bounded between the constant bounds from a to b, and it's x that is now between functions of f, g of y and h of y. We have made no change to z. In that case, dv would be summarized as dz dx dy. Right? In our third organization, right, what we consider there doing, right, is leaving x bounded between the values of a and b, but consider having z and y change roles. Now, if x is still bounded between the constants a and b, z then will be bounded between the functions g of x and h of x, and y will be then bounded between the functions of m and n, which are functions in terms of now x and z. And when that organization or that description of d evolves, right, we would say that our order of integration for dv would happen in the order dy, dz, dx. The innermost with respect to y, the middle in terms of z, and the end or the outside in terms of x. Right? In our fourth case, we consider the case given above for case 3, but swap the roles of z and y. Z and x, leaving y unchanged. If we swap the roles of z and x, z being bounded between constants a and b, and x being bounded between these functions of z, y remaining between these multivariable functions of m and n, all right, or functions of x and z, then dz is summarized as dy dx dz, right, where we see the dx and the dz changing order in that integration. Right? In the fifth and sixth cases, right, what happens there is I now think about x being our innermost integration, right? X being bounded between functions y and z in each case, but then region R being descriptions that occur in the yz plane. Bounded either between values of y, constant values of y from a to b, and z values between functions of y, g of y, and h of y, or z being bounded between constant values a and b, and y being bounded between these functions of z. Right? In case 5, our order is dx, dz, dy, whereas in case 6, that would be dx, dy, dz, where again, dx is still going to be our first integration in the iterative process, but it's dy and dz that change their order of integration. All right? If we consider an example, we ought to take note, before we get into that example, that lastly, as with double integration, the order of the integration really depends upon the information given in the problem and the efficiency of the triple integration it presents. Right? What we're going to see is that there is more than one way to carry out a triple integral over a region D. Right? What order we choose sometimes depends upon the information given in the problem and what's going to be the efficiency of that calculation. Right? Some calculations will be more efficient than others. Some will be possible and some might be impossible. What we're looking for is the way that is going to get us to the answer the quickest, right? And is going to be an answer that we can find, right? Given us an answer that actually results in a definitive solution, right? Where this all develops from, folks, how you recognize this is really with practice. It's going to take, again, a lot of that practice, so make sure you're putting that time in, right? If I do consider a case of switching around our variables, right? Here's a case where we might consider changing the order of integration, illustrated by this triple integral, right? Where dv is described by the order dy, well, I should say in our given case is described by the order dz, dy, dx, into an order where dv is described by the order dy, dz, and dx, where in a sense we switch around this order of dz and dy in this integration. All right? How we approach this, folks, is first of all, we take note of the region that we're currently describing with this triple integral calculation. All right? Note from this description of dv and the value of, well, I should say dz, dy, dx, d must be described this way. This must be our solids description for D, region D. Z must be bounded between these multivariable functions of x and y, which you'll notice one of them is a constant and the other only involves y, which implies a cylindrical region of space, right, in 3 dimensions. Y is bounded between constant values from -2 to 2, which we see here in the description, and as expected with x as the outermost integral, that's bounded between the constant values of 0 to 1. Part of changing the order of an integration is to understand the solid over which you're integrating. Here I have an illustration of this solid over which we're integrating. If I blow up the picture slightly so we can see it perhaps a little bit more clearly here. This is our x-axis, this is our z-axis, and this is our y-axis. As we can see, this solid is forming over values of x from 0 to 1. It is also forming over values of y from -2 to 2, where our z value depends upon just strictly our y value. And if you notice, the smallest z is 0, which defines the xy plane itself. And you'll notice that xy plane itself, this whole solid, is forming over a region R, where region R is described by this rectangular region given by the bounds of x and y. As for the upper bound on z, z is upper bounded by the square root of 4 minus y squared, where if we spend a little moment there and consider what kind of surface that describes what we would call a cylindrical shape. If we actually squared both sides, we would find z squared would be equal to 4 minus y squared, or z squared plus y squared would equal 4. We would have a description of a circle in the yz plane, where we're everything within that circle in the yz plane. And actually, you can see that circle here, that yz plane, maybe on this forward face, right, where we're interested in the region in that circle, right, starting at 0 and going up to that outer bound, right, where z would be equal to the square root of 4 minus y squared. This whole solid, again, forming over this region of R. All right? So to begin with, in terms of changing your order, you do want to try to understand your region, right? Where now, given the integration that we have, right, what we're asked to do, right, if this calculation is going to be transformed into the integration involving the summary of dv given by dv equal to dy, dz, dx, where we change the order in the descriptions of dy and dz, then in general, what we're looking for is a description of z that looks, or I should say a description of d that looks like this, where x is going to remain between constant bounds of a and b, z might define itself between functional bounds of x, g of x and h of x, and now our descriptions of y have to occur between these multivariable functions of x and z. Let me just double check that there, right? And let me double check that in my 6 cases I didn't have those backwards real quick. No, it looks like I have them all right up here. Just in that translation down below, it must have. I don't think I copy and pasted. All right, I think those are all good. Okay. So we were back here. I just had to change that one. I was just checking above to see if I had to change that in the one above, and I don't think I copy and pasted it. I think I brought that down from above. All right? Where if we think about region R, and this is part of the process, folks, is as you start to define your new region of D, I often start with thinking about how region R is defined, right? This being our description of region R. And in this case, if region R is going to be described by variables z and x, that's going to be a description that occurs in the xz plane. Now, if we look at our illustration of this region, that would be a region R illustrated right here. The xz plane is going to occur where y is equal to 0, where this solid is occurring over this xz plane, where y equals 0, described by this rectangular region here in that xz plane. And if we think about the dimensions of this rectangular region here found in this xz plane, that is a region where x again varies from 0 to 1, as it had done in the other rectangular region that we had in our initial setup, and z varies across these bounds from 0 to 2. I believe in terms of our rectangular region here, I did give us an illustration. Right? If we consider region R as this region of space in 2 dimensions described by x and z, it's this description right here. Right? Or formally we can say this about x and z. That is the region of space describing R now for this new setup. All right. So what we have left to do, that does give us our first 2 set of bounds in our integration in that intersection describing region D. What we need to now come up with is our understanding of y. What is y stuck between? All right. What y is going to be stuck between, if we're looking at over this region here, this region R in the xz plane where y equals 0, it's going to be stuck on the lower end between this semicircle, or I should say this cylindrical portion here, right, seen by this quarter of the cylinder on the lower end, and on the upper end by this region seen up here, the other quarter of this cylindrical space. What describes those bounds on y are going to be functions technically only given by z. Notice the relationship described by these bounds only depends upon y and z in our initial description. So when we consider changing the roles of y and z in this organization, y is only going to be dependent upon some description of z. And if we think about that description of z here, all right, let me scroll this up into place. We might say this overall about the values of z. All right. As for y in D, note over region R in the xz plane, the values of y depends upon only the value of z, where y is actually stuck between the lower quarter of that cylinder and the upper quarter of that cylinder. So when we think about region D now in this setup, it is described by this intersection of surfaces. Well, intersection of bounds on x, z, and y. All right? That is our transformation into a summary of dv given by dy, dz, dx. Right? And I do think I approach that here. I say, so d is given by this, and our triple integral, right? We might say over, let me be more general here, dv would be equal to this calculation here. All right? Where I went ahead and dropped in an argument of 1 into that. And the reason I dropped an argument of 1 into that is I did want to point out something here. Again, I'll try to develop this in a set of notes, but we do have a bit of an analogous idea. And that is if our surface here is described in in 4-dimensional space, our hypersurface is described in 4-dimensional space as being a constant value of just 1, right? What we might call I don't know how we would say this, the hyper height of that surface would also just be 1 in value, and 1 times that hyperheight times the volume of its, what, hyperbase, the solid D, right, would give the overall would just yield the volume of D, right? So one thing I would note is because our argument is just 1 here, right, the entire thing we're actually calculating is also going to correspond to just the volume of D. What we are calculating is just the volume of this three-dimensional region of space. And what we ought to note is that volume does involve a little symmetry. Right? Symmetry that happens across this location where y equals 0. That happens on either side of our regional description for R. The region below appears symmetrical to the region above R. So if we think about calculating the volume of this solid D, we could consider just the volume above region R given on the right side here and doubling it in value, right? Exploiting a little bit of symmetry in our illustration. So if I bring this into picture, right, this makes this calculation a little easier, right? This might be considered a bit more of an efficient calculation than the one we started with. Since f of x comma y comma z equal to 1 illustrates symmetry over D, the triple integral calculation could actually be approached as this. Just double half of that description of D, the upper half, from 0 to the square root of 4 minus z squared. All right? Where if I now start that iterative process, scrolled out too far here. All right? I'm sorry this is a long set of notes. We're just about wrapped up here, folks. So bear with me, right? So if we do an iterative integration in this case, if we integrate first with respect to y, the value of 1, that would just have an antiderivative of y that we would evaluate across these bounds, which would just leave behind the upper bound. All right? So we see that in the next 2 steps here. The antiderivative of 1 is y that we're going to evaluate across these bounds, which is just really going to leave behind the upper bound. Or now I'm going to evaluate that square root of 4 minus z squared with respect to z. Now you're going to say to yourself, how do I do that? Keep in mind this would involve, if you want to get into it, it would involve a little trigonometric substitution. But what I always suggest doing before you dive into a trigonometric substitution is you check the integration tables. And actually, if you go back and you look at the integration tables, there's a result in our tables for this specific case of an integrand. And if I apply the result from our integration table, this would be the antiderivative I would find in the table. Now, in our particular example, what table value I used from our book, it was table number value number 61, right? If you're looking back for what case I used in the table. But from the integration tables, number 61, I used this result, which I'm now just going to evaluate from 0 to 2. At the value at 2, let's be careful here. 2 divided by 2 is 1. So I should be careful. Yeah, that would be 1. But what we notice is when I plug in 2 here, that becomes 4. 4 minus 4 is 0. Square root of 0 is 0. And it would be 0 times that value of 1. So this first term evaluated at 2 becomes 0 and is added to this quantity at 2. Now if I plug in 2 here, 2 divided by 2 is 1. We would have the sine inverse of 1 times 2. That would be 2 times the sine inverse of 1. Now, did I simplify that? If I haven't simplified that in the next step, I will. But take note, what is the sine inverse of 1? We're saying, what angle measurement gives us a sine value of 1 from negative pi over 2 to pi over 2? This argument is pi over 2. Right? The sine inverse of 1 is equivalent to pi over 2. So we'll substitute that in the next step and cancel it with 2. But before I move on, what I want to do is subtract that from what I get if I evaluate this at the lower bound of 0. Now, if I substitute in 0 here, 0 divided by 2 is 0. So 0 times this other factor in the first term would also just become 0. And that would be added to, now if I plug in 0 here for z, 0 divided by 2 is 0. And we ask ourselves, what's the sine inverse of 0? What angle between negative pi over 2 and pi over 2 gives us the sine, whose sine value is 0, and that is a 0 radian angle. So the answer here at 0 is also just 0 for that entire quantity, so times that 2 becomes just 0. And what we're left with is just this argument, where I said this is equivalent to pi over 2. So if I bring that into view, I do think I make those judgments. Yep. And I actually finish this in one line here. All right. As I noted, this quantity here by the sine inverse is going to be pi over 2. All right. Times this 2 will simplify out to just be pi, which I can bring out as a constant multiple. And I am now just integrating from 0 to 1 the argument of what remains is 1 across the bounds from 0 to 1. And that antiderivative is simply x, where evaluated from 0 to 1 is simply 1, times 2 pi becomes 2 pi units to the 4th power. All right? Or the value of the triple integral is 2 pi here, folks. Right? Geometrically interpreting it as a hypernet volume, that would be 2 pi unit, quartic units, we might say. All right? I do take note, one more thing here. Lastly, I believe I say here. Lastly, note, analogous to double integrals, the single integral and single integrals, applying the triple integral to d with respect to the volume of d to a multivariable function f which equals 1 also just yields the volume of d. What we calculated up here not only was the value of this hypernet volume, but we also calculated what's known as just the volume of d. All right? And that is similar to when we apply it the double integral, that just gives us the area of R. Right? See, this is the volume of d. This is going to give us the area of R, whereas this is going to tell me the length of x from a to b if I think of the single integral in its calculation. Right? This does have a little nicer generalization when we actually get up and introduce the linear integral in chapter 17. We can make a connection back to this idea a little bit more naturally. All right? And when we think about our previous example, right? Note in the previous example we calculated this, which was equal to 2 pi units to the 4th power, right? When we considered its hypernet volume interpretation. But as we had noted above, this is also the volume of D. It's the volume of all this space, right? Where the volume of all this space would actually be 2 pi units cubed, right? We get 2 pi units cubed because the hyper height, we had said, was equal to 1 units, right? And if we think of this as being 2 pi units cubed, note this triple integral calculation correlates with the volume of the solid illustrated by region D, which is the volume of half a cylinder. All right? Given by the, we might point out, is the geometrical formula. Volume for half a cylinder is 1/2 pi times its radius squared times its height. Now this is a cylinder that has a height of 1 unit and a radius of 2 units. So when we substitute in those values, volume would be 1/2 times 4 pi times 1, which is 2 pi units cubed. And as we do see, that triple integral calculation that gave us 2 pi quartic units does equate to the measurement we would have for the volume of region D, which would be 2 pi cubic units found by the volume, given by the geometrical formula for half a cylinder. All right. As I noted, folks, this was a little longer lecture here. There was a lot going on in triple integrals. But I hope it was thorough. I hope it gave you a couple of good examples and gave you things to think about, and certainly gave you some direction to begin heading in terms of your practice. And that's the biggest thing here, folks. It's putting in the practice. Start with the simple cases. Some of the work with the cases of constant bounds and work your way up to variable bounds. See some success. Check your answer. See some success. It's going to build up that confidence so that you're more likely to tackle those more challenging questions with greater accuracy. All right, folks. Hope you're hanging in there. This was a long lecture. I did take a couple of breaks in there. Hopefully you don't notice too many of those. But yes, I'll be posting this up soon, and I hope to see you all very soon. Again, hang in there, and I'll catch you next time.